magnetostratigraphy and radiometric dating. In addition to the comments made above by Rushdie said, lithostratigraphic, biostratigraphic and chronostratigraphic units have frequently been confused, with the result that the lack of precision in definitions has produced a nomenclature which is often difficult to use in a more exact chronological framework. Then again, certain features of the magnetic field, such as slope or intensity, seem to be very closely related to climatic features. Figures 16.1 and 16.2, from Vorlin et al., 1974. Quaternary glaciations and dating. It is likely that at least 12 considerable cold changes have been recorded in the continuous deposits accumulated at the bottom of the oceans during the Quaternary. See Figure 16.2. Only about 8 have been recognized in the continental deposits of northern Europe. The HE fluvial terraces and glacial deposits of the Alpine region are related to 4 or 6 generally accepted glaciations: GBNZ, Mindel, Ris, WURM and Donor, Biber, each of which may comprise a number of stages. The discontinuous nature of the continental evidence makes it difficult, and often illusory, to correlate glacial periods in distant regions when they are not situated with certainty on a magnetochronological or radiometric. 372. COREVZ2 IMTVNSIDY01. 300. 400. L EMU/GRX 10 degrees 23 II. COREV 12 122 80 18 COLD. Figure 16. Graphs showing analogies between oxygen isotopes or temperature variations and the intensity of the Earth's magnetic field, in a deep-sea core, for the last 5,000 years after Vorlin, Ericsson 5 pounds Vorlin, 1974. 373. Core V16 to 205 Core V16 to 205 Inclination degrees ratios cold. Figure 16.2 Graphs showing analogies between temperatures indicated by the micro/ana and the magnetic inclination for the last 2 million years after Vorlin et al., 974. 374. Chronological framework, African pluvial and glacial epochs. Scale. In point of fact, the accepted chronology for the alpine glaciations is vague. The terms GBNZ, Mindel, Ris, WURM and Biber have been used in various regions to denote formations which are not synchronous. Thus, according to the potassium-argon dating of the volcanic rocks intercalated in the Rhine terraces, the formations known as Mindel I and II appear to be 300,000 and 260,000 years old, and the terraces known as GBNZ I and II 420,000 and 340,000 years old. But the same term GBNZ is sometimes applied to the cold period preceding the Cambrian, which would therefore be from 900,000 to 130,000 years old, coinciding with a cold period preceding the Jeremy Low event in the undersea course. According to the latter interpretation, the Donor, the preceding cold period, should include the Gilsa event and be the equivalent of the Eburonian. It will be understood from this example how dangerous it is to transfer from one region to another a chronology based on continental climatic successions, if one retraces the number of cold occurrences identified and reviews the arbitrary nomenclature attributed to them. The divergences render precarious any correlation of evidence of alpine glaciations with the successive cold changes measured in ocean course. Complete and continuous recording of all climatic phenomena, on the one hand, and of magnetostratigraphic and radiometric references, on the other, is essential if a stratigraphy scale is to be worked out even approximately and if valid comparisons between two regions are to be made possible. The Hema to Yama-Bru magnetic reversal 690,000 years was identified in the Cambrian stage by means of palynology, and the Gilsa occurrence 790,000 years in the Eburonian stage. Vangmont, France, 1971. Quaternary transgressions and dating. Each glaciation brings about a glaciocutatic regression of the sea, which may amount to 100 meters or so. Marine regressions brought about by the melting of ice therefore make it possible in littoral zones to link climatostratigraphic chronology with the chronology of marine cycles. In regions where the marine formations are Coral in Barbados, Bermudas, NEW Guinea, the Red Sea dating by methods based on the disequilibrium of uranium applied to the aragonite of corals has made it possible to ascertain the age of marine transgressions from the last interglacials 200,000, 120,000, 105,000, 85,000 years BP approximately. Within the margin of physical error of the various radiometric dating methods, it is observed that these high sea levels correspond fairly well with the higher temperature phases indicated by the marine microfauna, pollen and oxygen isotopes. 375. Methodology and African prehistory. Mechanisms of global climatology. Climate does not constitute a simple means of chronological correlation. Owing to the complexity of the factors entering into it at any given moment or over a period lasting centuries or millennia, there can be no question of using data which have not been properly dated as stratigraphy or chronological criteria. The facts leading to these observations are of two kinds: a knowledge of the global evolution of climate over a few decades or a few centuries, on the basis of historical data, shows how complex the problem is on a global scale. One has to know the evolution of all factors: the solar constant, ocean circulation, the situation of polar fronts, distribution of temperatures, rainfalls, not only their averages but their variability. To a knowledge of the variations of certain climatic factors over the past 25,000 years or so, and of the Pleistocene and Holocene obtained by means of radiometric measurements, shows us, on the one hand, the rapidity of the changes concerning which reliable evidence exists, and, on the other hand, the complexity of correlations on a global scale. The time scale taken into consideration then plays a major role. The climatic system, as defined by the National Academy of Sciences, Washington 1975, is made up of the properties and processes which are responsible for the climate and its variations: thermal properties, temperature of air, water, ice, soils, kinematic properties, wind, ocean currents, ice movements, etc., aqueous properties, humidity of the air, clouds, surface water or groundwater, ice, etc., static properties, pressure, density of the oceans, salinity, etc., has also the geometric limits and constants of the system. All the variables in the system are interconnected by the physical processes which occur in it: precipitation, evaporation, radiation, transfer, convection, turbulence. The physical components of the climatic system are atmosphere, hygrosphere, cryosphere, lithosphere, biosphere. The physical processes responsible for climate might be expressed quantitatively by dynamic equations of movement, the equation of thermodynamic energy and the equation of continuity of mass and water. Climatic variations will be complex in as much as there might be considerable interaction between the elements in the climatic system. So the causes of climatic changes are many and varied, particularly having regard to the time scale involved and the interaction mechanisms feedback. Oceans play a considerable part in climatic changes through the processes at the air-water interface, which govern exchanges of heat, humidity and energy. These preliminary considerations go to show that the climatostratigraphy. 376. Chronological framework. African pluvial and glacial epochs of the Quaternary has been a stage, a necessary approximation, but that it is gradually making way for an attempt to understand the mechanisms involved in particular situations over different periods of time. For this reason, several examples of recent results bearing on the present era, the Holocene, the Pleistocene and the Plio-Pleistocene, will be examined. Climatology in Africa today and in the recent past. In Africa, the annual rhythm of alternation of a dry season and a rainy season in the intertropical zone is bound up with the displacement of the intertropical convergence zone ITCZ. As summed up recently by J. Maley 1973 and L. Dory 1974, the ITCZ represents the place where a monsoon humid air coming from the equatorial regions or the maritime trade wind from the southern hemisphere and the harmattan dry air from the Sahara meet. The ITCZ, which lies approximately west-east, moves from the south to the north during the spring and the first 2 months of summer, then from north to south. This seasonal oscillation occurs between 4 degrees N and 23 degrees N. The surface of discontinuity between the humid air and the dry air slowly rises north to south. The humid bank of a monsoon is only a very thin cold corner towards the north in summer, not giving much precipitation. The humid air has to be from 1200 to 1500 meters thick for precipitations of any importance to occur. These conditions are found only from 200 to 300 kilometers south of the ITCZ Eldari ice, 1974. The position of the ITCZ varies considerably, not only from one season to another, but also from day to day, as a result of the field of pressure of the whole of Africa and the Atlantic Ocean. As shown by Pelo board 1970, the original thrust from the southern Atlantic combined with the activity of the South Polar Front represents the essential motive force pushing the convergence zone northwards. The GHA southward withdrawal of the ITCZ in September would then be due to the weakening of the South Atlantic anticyclone and the influence of the Northern Hemisphere. The GHA occasional intervention of northern air dried after its transit over the Sahara gives only a little rain on the Sahara mountain ranges. Conversely, the southerly air, after crossing the ocean, brings potential humidity. The present climatic crisis in the Sahel zone is due to the fact that the ITCZ has remained from 30 to 40 farther south than its average position. During the wet decade of 1950-9, on the other hand, the Sahara shrank. As J. Maley has shown 1973, the humid phase coincided with a drop in the maximum temperatures on its southern borders. Then OW, the colder the polar air, the stronger the polar fronts and the farther they extend towards the equator. In this connection, Maley 1973 distinguished two mechanisms, namely, that of the glacial periods and the one made evident in our own time. In the former case, the area of the ice sheets in the northern hemisphere increased considerably, while the 377 methodology and African prehistory Antarctic ice sheet would appear to have varied little. The North Polar Front then had a preponderant influence, driving a monsoon far south in summer. Aridification then went hand in hand with glacial expansion. With the warmer temperatures of the Holocene period before 5000 to 4000 BP, the center of polar action weakened. During the northern summer, the regression of the North Polar Front favored the extension of a monsoon north of the equator, while the South Polar Front drove the subtropical anticyclones towards the equator. During the northern winter, the polar front could again extend its action over the Sahara and bring rain. The occurrence of rain both in summer and in winter would explain the humid climate which prevailed in the southern Sahara and the receding of the desert during the first half of the Holocene. Over the past 5,000 years, the regression of the Arctic ice sheet has reduced the strength of the North Polar Front, while the center of action in the Antarctic has also diminished in strength. The thrust of a monsoon and the diminishing effects of the northern polar air on the Sahara at the same time, would thus explain the gradual aridification of the Sahara. These meteorological mechanisms and why help us to understand the climatic changes which occurred in Africa during the Quaternary dating and climates over the past 25,000 years. The last 25,000 years of the Quaternary and of the Pleistocene and Holocene afford a recent and now well-documented example of a vast glacial advance and of the ensuing recession up to the present interglacial. During the same period, the intertropical regions underwent extreme aridity, followed by a humid phase, then aridification again. This is the only climatic fluctuation which can be studied over a period of several centuries or several millennia, permitting comparison of the elements of the climatic system and its variations in many regions of the globe situated at nearly all latitudes. In addition, for this period the indications supplied by pollen, diatoms and pore identical to the modern species allow of quantifying the magnitude of the variations of the geographical environment with precision. Besides, the average sea level is well enough known for us always to be able to have some idea of the general volume of the ice and the isotopic relationships of the oxygen in the principal reservoirs. Oceans, Ice Seymour, 1975. As regards the African Sahara, since the first comprehensive surveys based on radiocarbon dating Butzer, 1961, Morneau, 1963, 4, 1967 and 1969. The most recent studies which can serve as a basis for a detailed chronology of climatic variations are those of M. Servant and S. Servant, in the Chad and Niger, F. Gas, in Afar, and the teams of Van Inderen Becker and Livingstone, of Richardson, of Williams, of Wickens, and so on in East Africa. Their findings are comparable with those of many surveys in regions in high latitudes, in particular those of Bilichko, Driemannes, 378. Chronological framework, African pluvial and glacial epochs. And so on. The Atlantic Ocean region is known as a whole through the work of the CLIM Page 1 group and McElntire, while the Southern Hemisphere is known through the publications of Van der HMMEN, Williams, Solar and others. To situate the evolution of the climate of Africa over the past 25,000 years in a global perspective, several chronological stages may be distinguished. 25,000 to 18,000 years BP. High latitudes. The period of time covered by the years 25,000 to 18,000 BP corresponds to the end of the maximum extension of the ice sheets in the northern hemisphere. This last extension of the WRM glaciation Wisconsin-Whitesill and Valdez covered with ice in area representing from 90 to 95% of that covered during all the previous quaternary glaciations. Flint, 1971. It is thus a very representative model of a glaciation. In periglacial zones the permafrost soil permanently frozen all the year round seems to have been more extensive than it was during other glaciations. Bilichko, 1973 and 1975. The HE presence of this extensive permafrost on the continent would appear to have been associated with sea ice, also very extensive in the Arctic oceans, which was a factor in reducing evaporation at the air-sea interface. The oceans combined with the reduction of free surface due to sea ice, the lowering of mean sea level, going down from about -50 to about -100 meters, contributed to reducing the area of the oceans by a further 10% or so. At the end of the period under consideration nearly all the continental shelves had emerged. Research workers in the CLIMP group McElntire et al., 1974 and 1976, Hayes, in CLIMP, and so on have been able to construct charts of the temperatures of the surface waters of the Atlantic Ocean for the time of the glacial maximum 18,000 BP. Figure 16.3. In comparison with charts for existing situations which are those of an interglacial. These charts show the general average of temperature differences which is only 2 to 5 degrees between the glacial maximum and the present interglacial. However, the distribution of temperature differences shows the maximum at medium latitudes differences of from 6 degrees to 0 degrees and much smaller differences less than 30 at intertropical latitudes. Figures 16.4 and 16.5. For instance, at the point 50 degrees and 30 degrees W, the surface temperature was from 7 to 3 degrees to 12 to 7 degrees lower in winter 18,000 Oregon 17,000 years ago than it is at present. In summer the difference dropped from 1 to 2 to 6 to 6 degrees. CLIMP, 1974. In both hemispheres the migration of polar waters was the dominant factor in this glacial epoch. In the North and Atlantic, the polar waters came 1. CLIMP Climatic Long-Range Interpretation, Mapping and Prediction of the International Decade of Ocean Exploration IDOE. 379. Methodology and African Prehistory. 80-60 degrees 40 degrees 20 degrees 20 degrees. Figure 16.3 Surface Maker isotherm map of the Atlantic Ocean for February, 18,000 BP. The dashed isotherms are interpretative. The major continental ice masses are delineated by hatched borders, the permanent pack ice by granulate borders. The glacial shoreline is drawn to a sea level of -85 meters from today after McElntire et al., 1c75, down as far as the 42nd parallel from a position near the present one, about 60 degrees and giving rise to a rapid temperature gradient south of the 42nd parallel, which was therefore the probable axis of the westerlies in the glacial epoch. South of this limit the pattern was much the same as it is now, but it is observed that the isotherms, running parallel to the coasts of Africa, reveal the existence there, particularly in winter, of relatively cool waters due to an increased upwelling. Gardner and Hayes, 1975. The polar fronts and the axis of the westerlies moved more than 2,000 kilometers towards the equator in the North Atlantic and only 600 kilometers in the South Atlantic. In the Pacific Ocean the polar fronts seem to have moved very little in glacial periods. This would explain the diminished penetration of a monsoon over the Sahara Sea. Maley, 1973, pages 7 to 8 and the arid state of the Sahel zone at the end of the glacial period. 380. 38 High. Chronological framework, African pluvial and glacial epochs. Africa in the southern Sahara and the Sahel regions. The general evolution of the climate over the past 25,000 years shows a fairly similar trend from the Atlantic coasts to the Red Sea. This period of time comprises the end of a humid epoch of the Upper Pleistocene which lasted from about 30,000 to 20,000 years BP and the beginning of an arid epoch, which ended around 12,000 BP. The study of lacustrine deposits in the Chad Basin has shown that the relationship between precipitation and evaporation P/U was sufficient to enable quite extensive lakes to remain in existence from 40,000 years BP to about 20,000 years m. Servant, 1973. During the ensuing 8 millennia the arid zone extended, spreading more than 400 kilometers farther south than its present limits. This transition from a lacustrine episode to a very arid epoch is also observable in the deposits of the FR lakes, where F. gas showed the existence of 3 lacustrine epochs in the Upper Pleistocene. Between 20,000 and 17,000 years BP the lacustrine environment deteriorated and the dried-up bed of Lake Abiy was occupied by granite gas, 1975. Reviewing the most recent literature, M. Servant 1973 and F. Gas 1975 note a quite comparable evolution in the case of other East African lakes at various altitudes and latitudes. The work of Richardson, Kendall, Butzer and others, Grove and others, Livingstone, on Lake Turkana, Nakuru, Naivasha, Magaday, Albert, etc. This comparison is summed up in Figure 16.6, which shows a fairly parallel evolution for 12 African lakes. 18,000 to 12,000 years BP. High latitudes in regions at high latitudes this period corresponds to the end of the glacial maximum and to the deglaciation. The ice caps which covered eastern North America and Scandinavia and which reached their greatest extent between 22,000 and 18,000 years BP began to melt immediately after that time. That of the North American Cordillera reached its maximum only 14,000 years BP and disappeared around 10,000 years BP. The general deglaciation began, therefore, around 14,000 years BP. In the southern hemisphere, on the other hand, the continental ice cap in the eastern Antarctic seems to have varied little, while the one in the western Antarctic, with its base below sea level, seems to have dwindled quite considerably. National Academy of Sciences, Washington, 1975. Oceans. The huge surfaces covered with sea ice certainly disappeared with the very rapid rise of the sea level following deglaciation. This rise attained 1 to 5 meters per century on the average between 15,000 and 12,000 years BP, by 383. Chronological framework, African pluvial and glacial epochs. Which time half, if not two-thirds, of the rise had occurred. At the same time the polar waters of the Atlantic returned to more northerly latitudes. Africa. The great aridity of the period comprised between 18 and 12,000 years BP, which extended over a large part of Africa, is the best documented phenomenon. It is well evidenced by the graphs showing the evolution of lake levels in Niger and Chad. Servant, 1973 in Fard Gas, 1975 in Sudan. Williams, 1975, Wickens, 1975 and so on. The HE disappearance of vegetation enabled the winds to drive the dune forward from 400 to 800 kilometers in the direction of the equator and on the emerged continental shelves. There is no doubt that over several millennia the Sahara, thus extended, constituted a more formidable barrier to man than does the Sahara of today. This aridification seems to have been extremely general and there are many indications that the intertropical zones as a whole dried up to some extent in Africa. Diploe, Vans in Becker, etc. in Williams, 1975 and in Asia, particularly in Viasink, 1973. Williams 1975 recently reviewed the literature concerning this arid epoch and showed its exceptional and approximately synchronous extension till the Mediterranean basin. Although the evolution of the climate during the last glaciation some 1,000 years ago seems fairly complicated in the Mediterranean basin, see page 392 below. Palynological findings Donati, 1966 and pedological findings Rodenberg, 1970 indicate that at the glacial maximum the climate was dry and cool. The Mediterranean zone was occupied by a very dry steppe between 16,000 and 13,000 years BP and calcareous crusts developed on the soils. Southern Hemisphere in Australia, the study of pollens indicates that there was a gradual drop in temperatures until about 18,000 Oregon 17000 years BP, while drought conditions became established and dunes extended over the emerged continental shelf. Goller et al., 1975. The HE glaciation occupied Tasmania and the Snowy Mountains while the South Australian lakes dried up around 16,000 years BP. Warmer conditions, indicated by a rise in altitude of the tree line, set in around 15,000 years BP, but the South Australian lakes only began to fill up again after 11,000 years BP. Goller et al., 1975. Van der HMME in 1974 and Williams 1975 have drawn attention to the analogies which characterize the climates of both hemispheres during the last glacial maximum around 18,000 years BP. The general aridity persisted during several millennia in all regions of the globe lying at low latitudes, with the exception of the southwest of the United States. 385. Methodology and African prehistory. 12,000 years BP to the present high latitudes. This period is characterized by the end of the glaciation and a distinct rise in temperatures culminating between 7,500 and 4,500 years BP. The climatic optimum, still referred to in Europe as the Atlantic period. The HE ice cap on the Cordillera melted very rapidly and disappeared around 10,000 years BP. The one in Scandinavia disappeared shortly afterwards 9,000 years BP. Distinct rapid fluctuations at intervals of about 2,500 years as, for instance, the cooler conditions of the New Dryas between 10,800 and 10,100 years BP have been noted. The situation in respect of glaciation began to be comparable with that prevailing at present around 8,500 years BP in Northern Europe and around 7,000 years BP in North America. Nat. Akkad. SEI. 1975. At that time, too, the ice sheet in the west of the Antarctic receded. Oceans. The rise in sea level, which reflects the average melting state of the world's glaciers, was still very rapid between 12,000 and 7,000 years BP. More than 1 meter per century on the average, but with a considerable deceleration or a fall around 11,000 years BP. The HE oceans seem to have reached a level very close to the existing level after 6,000 years BP and to have oscillated only a few meters above and below it ever since. In addition to this general trend, sea level fluctuates in accordance with general climatic variations. Morner, 1973. The zones in which marine sedimentation was reasonably rapid, zones studied by Vorlin and Eriksson, also enabled us to follow changes in the distribution of foraminifer, in particular, the variation of the percentage of sinistral globerotalia truncatulinoides. According to Morner 1973, the peaks in the corresponding curves could reflect the peaks in the curves of climatic changes recorded by means of isotopic surveys of ice in Greenland, palynology scales and fluctuations in sea level. However, the limit of precision of the radiometric dating method is reached here and linear interpolations are required between the dates, the variations in the sedimentation rates being taken into account. Besides, the distortion of the chronological scale of carbon-14 in relation to the time scale makes corrections necessary, and it is tricky to correlate phenomena which existed for only a century or two. Africa. After the extreme aridity of the period extending from 16,000 to 14,000 years BP and from 12,000 years BP onwards, the lakes in the Saharan regions expanded in a remarkable fashion from the Atlantic coasts to the Red Sea. In nearly all the low-lying regions, lacustrine deposits, often consisting of diatoms, are to be observed. 386. 387. Methodology and African prehistory. In Niger and Chad, M. Servant 1973 worked out a continuous curve of the P/E ratio figure 16.7 on the basis of a study of various types of lake, taking into account their source of supply and their hydrogeological and geomorphological situation. This climatic curve illustrates the major oscillations, which seem to have a general character: great expansion of the lakes around 8,500 years BP, to diminution around 4,000 and minor fluctuations after 3,000 years BP. These major oscillations affected the various lakes in Afar, too, though with some minor differences due to their sources of supply. Gas, 1975 figure 16.8. The definite analogy is to be observed between the Chad curve and the humidity curve for the Siberian continental zone. A study of the other African lakes shows a fairly comparable line of evolution. Figure 16.6. Livingstone and Van Backer consider that there is a fairly close parallelism between the climatic evolution of East Africa and that of Europe. The expansion of the Sahara Lakes up to 8,000 years BP seems to be connected with the better distribution of rainfall throughout the year and cloud cover thick enough to reduce evaporation. M. Servant 1973 suggests that atmospheric circulation was different then from what it is now. The presence of several levels of cold climate diatoms leads him to postulate possible intrusions of polar air over the Sahara. The present climatic mechanism would appear to have become established only after 7,000 years BP. Southern Hemisphere in the north of Australia and in New Guinea the glaciers disappeared 8,000 years BP. Mount Wilhelm while rainfall increased, with minor fluctuations, according to Doller and others 1975. Between 8,000 and 5,000 years BP the average temperature would appear to have been 1 degrees or 2 degrees higher than at present. The climatic optimum hypsothermal would appear to be a global phenomenon, while the rainforest between 7,000 and 3,000 years BP enjoyed the most favorable conditions for its development since the preceding interglacial, before 60,000 years BP. Similarly, the lakes in the south of Australia, which had dried up 15,000 years BP, began to fill again around 11,000 years BP and attained high levels around 8,000 and 3,000 years BP. It seems likely that in general temperatures rose and humidity increased in low-latitude zones during the first half of the last 12,000 years, leading to conditions characteristic of the present interglacial. Conclusion with regard to the climatic chronology of the past 25,000 years. This period gives us a picture of the climatic evolution during the glacial maximum at the end of a glacial period and during a deglaciation leading to diminution just before 7,000 BP, another expansion around 6,500, 388 p/e, 1/1 OL, OLE, 404, 300, 51 240 OJ, 200, 100, -100, -155, -80, /W/J. Asterisk 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 number sign asterisk 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 I asterisk 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 Lake Thabie, Lake Hamadodi, Lake Assab Central the Farm, asterisk 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 Lake Freer Northern the Farm. Oscillation, P/E in the Chap Basin. TT 11,000 10,000 9,000 8,000 7,000 6,000 5,000 4,000 3,000 2,000 1,000 0 age in years B.P. Figure 16.8 Variations in lake level in the Afar basins. The curves for Lake Thabie, Lake Hamadodi and Lake Assab, situated in central Afar, are represented on the top part of the graph. The curve for Lake Freer is separate. Comparison could be made with the curve in variation of the P/E in the Chap Basin at Gas, 975, 389. Methodology and African prehistory. An interglacial the present. This model of half a deglaciation cycle shows generalized aridity lasting about 5,000 years in Africa and characterizing the end of a glaciation, followed by a humid epoch of comparable duration, fluctuating but gradually reverting to an arid stage. These climatic pulsations can be explained on a time scale of 20,000 years by the displacement of the polar fronts and their effects on the intertropical front, and by the two extreme types of circulation, rapid or slow. It is also likely that this model is representative of other comparable situations on the same scale as the quaternary, that is, similar in duration and amplitude. However, there is no justification for extrapolating to the whole of a glacial period lasting 1,000 years, and still less to all the quaternary glaciations, covering the period of several million years. For this reason the chronology of a glacial period will now be examined as a whole. Dating and climates over the past 130,000 years. The past 130,000 years upper Pleistocene afford an opportunity of studying the climato-stratigraphic model on the scale of a complete glacial/interglacial period. The chronology of this period far exceeds the reach of the radiocarbon dating, which has enabled us to establish a fairly accurate succession to within a century or at least a millennium for the last 25,000 years. However, this interval of time, corresponding to the last major interglacial eon before the present one and the last major glaciation worm, Wisconsin, White Solid N. Valde is fairly well known, the risk of error in dating being of the order of 10%, or 20% in the case of the remotest period. In point of fact, in oceans and sedimentary basins, extrapolation from known settling velocities, the application of methods involving the disequilibrium of uranium and potassium argon at the upper limit of its range, provide additional chronological data. Linear interpolation between dated points in a continuous sequence gives an approximate chronology. However, correlations over large periods cannot be made accurately enough for events which did not extend beyond several millennia. So it is mainly general trends over average periods 10,000 years which are best identified and can be compared from one region to another. High latitudes. The vegetation of the Nean interglacial indicates that during the warmest epochs soft het interglacial between about 125,000 and about 80,000 years BP, the temperature in Eurasia and North America was quite comparable with that of the Atlantic period between 7,000 and 5,000 years BP, that is, not much different from what it is now. Both these interglacials occurred suddenly after a considerable drop in temperatures. The last very cold stage of the RIS, 135,000 years BP, and the last very cold stage of the WRM, 20,000 years BP. 390. Chronological framework, African pluvial and glacial epochs. The ocean's variations in the level of the oceans reflect the two glacial maxima fairly well, dropping considerably endometer plus 20 meters for the second in the XIMUM around 20,000 to 18,000. The HE highest levels reached during the Nean interglacial and the present one are comparable to within 5%. Rises in sea level during the interim stages 45,000 and 30,000 years may have attained from 60 to 80% of the maximum rise the Inchirian in Mauritania, for instance. They confirm that an equivalent mass of ice melted during the interim stage. Africa. As in the case of the oceans, the repercussion of glacial phenomena was probably attenuated towards the intertropical latitudes. The HE differences between the temperatures of a glacial stage and those of an interglacial stage, from 50 to 0 degrees at average latitudes, may have been only from 2 degrees to 30 between the tropics. In Africa, the effects on the distribution and quantity of rainfall constitute the most readily observable phenomenon. Few regions in Africa possess a well-established radiometric chronology for the past 130,000 years. However, by sounding Lake Abyei, F-Gas 1975 was able to find evidence of 3 lacustrine stages in the upper Pleistocene, before the aridification from 20,000 to 14,000 years BP. These lacustrine stages were as follows: the period from 30,000 to 20,000 years BP. Temperate humid tropical climate separated from another expansion of the lakes from about 40,000 to 30,000 years BP by a considerable regression around 30,000 years BP, and earliest of all, the lacustrine stage from 50,000 to 60,000 years BP. Or perhaps from 60,000 to 80,000 corresponding to a cooler period, as indicated by the diatoms. The further indication concerning the climatic variations of uncertain date in the upper Pleistocene was yielded by a study of pollens in the upper valley of the Ouachita, where R. Bonfil 1974 found evidence of a climate distinctly more humid than the present climate, and perhaps colder, characterized by a steppe vegetation on high tablelands. Mediterranean basin situated between the two geographical zones studied above, the Mediterranean basin is an important climatic field, the evolution of which seems complex. In particular, the glaciations can no longer be considered as a simple cause for the establishment of a humid climate. Analyzing the palynological, micropaleontological and isotopic studies made in the eastern Mediterranean, in Greece and in Israel, by Emil Yanni I 955 greater than Bruno Gradini and Hermann Rosenberg 1969 with Gemster 1969 Van der HMMEN 1971 Rossignol 1969 Isard 1968 and Isard and Picard 1969 Farrand 1971 reached the conclusion that the drop in temperature during the last glaciation might have been 4 degrees in the case of the 391. Methodology and African prehistory. Air and from 50 to 0 degrees in the case of the sea. In Greece the drought was more marked during the glacial period, whereas the reverse was true on the coasts of Israel. On the other hand, a study of fragments of mammals rodents made by Chernow 1968, in Farrand, 1971 seems to indicate a gradual evolution of humid conditions in the direction of arid conditions during the past 80,000 years. Around 20,000 years BP the level of Lake Lasan, in Israel, dropped by 190 meters in 1,000 years as a result of drier conditions combined with a tectonic movement in the Dead Sea Rift and, as we have seen page 386, the end of the maximum extension of Quirinian. Cold was accompanied by cold and arid conditions throughout the Mediterranean basin. As with Africa, the complexity of the geoclimatic situation in the Mediterranean basin is such that further very detailed studies will be required to enable us to have a clear idea of the climatic evolution in the WRM period. Conclusion: with regard to dating and climates over the past 130,000 years, the last glacial period gives us a model of a complete climatic cycle on the scale of 100,000 or so years. Interglacial, glacial, interglacial with its fluctuations during and between those stages lasting something like 10,000 years. In Africa it is characterized by stages of lake expansion of comparable duration separated by stages of desiccation. Given our present state of knowledge, dating is not exact enough to allow of correlating cold or warm periods with any certainty with humid or dry periods in Africa. It is to be hoped that the work underway, supported by sections and samplings yielding a continuous succession of events, will enable us to answer this question in the future. Dating and climates over the past 350,000 years. The slow trend towards lower temperatures, which is a feature of the Quaternary, began nearly 55 million years ago. Cenozoic climatic decline at Akkad, SEI, 1975. The Antarctic ice sheet, which had already formed about 25 million years ago, increased considerably about 10 million years ago, then again about 5 or 4 million years ago, when it nearly attained its present volume. The Arctic ice sheet over the continents neighboring the North Atlantic appeared about 3 million years ago. The first big drop in the temperatures of the oceans generally began about 1800,000 years ago. Bandy, in Bishop and Miller, eds. 1972, shortly before the lowest level of the Calabrian marine stage, around the same time as the occurrence of the Gilsa 790,000 years ago. In Africa several regions, Chad, East Africa, and so on, have yielded a wealth of vertebrate fauna, first ascribed to the Villafranchian between 392. Chronological framework, African pluvial and glacial epochs. 3,300,000 and 1,700,000 or 1 million years ago. Some associations of mammals presuppose much more humid conditions than those which are a feature of the present environment of the deposits. They have therefore been regarded as marking pluvial periods in Africa. The most detailed stratigraphies, based on potassium argon and paleomagnetic dating, are those of the East African rift deposits. In this type of sedimentary filling the effect of the climate is more difficult to discern than that of tectonic and volcanic activity and the topographical changes which they produce, so that present authors have abandoned the attempt to establish a detailed climatic succession. On the other hand, the chronostratigraphy is well established and constitutes a world reference. In the various deposits of vertebrates and hominids in East Africa, figures 16.9 and 16.10 dated sedimentary successions are as follows. Onto Ethiopia: GHA Shungura Formation about 1,000 meters thick, extending from 3,200,000 to 8,000,000 million years ago. The Uthno Formation, from 3,100,000 to 2,700,000 years ago according to D. Heinzelin, Brown and Howell, 1971, Cottons, 1972, Bishop and Miller, 1972, Howell, 1972, Brown, 1972, 1975. A study of pollens in the Shungura Formation has revealed a considerable climatic change in the direction of drier conditions nearly 2 million years ago with the development of a grassy savanna Bonfil, 1973-1974. This change is confirmed by a study of the fauna. The suggestion might be made that it be paralleled with a world drop in the temperatures of the oceans 1,800,000 years ago. Oldaway Tanzania. The succession of the recognized formations and their chronology is as shown in Table 16.1. Table 16. by the succession of recognized formations and their chronology and due to beds -32,000 years ago. 0.400000 Mason J beds 600,000, bed IV 800,000, theft II 150,000, late Kanjaran J flash bed II 700,000, late Kamajone bed I 2,100,000 according to Leakey, Cook and Bishop, 1967, Howell, 1972, Hay, $197. 3540. Sudan. Number sign I tilde circumflex accent V dot slash I, underscore UGND slash backslash. 7 IAIEDHIOP via backslash slash. Slash CHKNYA. Figure 16.9. 394. Figure 16.9 Map of classical fossil-bearing localities of the Pliocene/Pleistocene era in East Africa. M. Murshi. U. Snow. S. Shungura formations. Lower Homo Basin. I. Illyria. J.F. Kubi Flora. Eastern sectors of the Rudolph area. L. Lotkogam. K. Canaposi Ikra. Of the Lower Kiro drainage. C. Chermahara. Ch. Chuso Anglo localities. Baringo Basin. K. Canum. Cabarondo Gulf. P. Penania. Natron Basin. Og. Oldaway Gorge. L.A. Litomal. Serengeti Plains. Base map largely after 1. 4 million East African Geology, Survey of Kenya after F. Clark Howell, 1972. Geological Sub-Saharan Europe and Time Divisions Africa Mediterranean Holocene 10 Cool IRs. Siberia and East Asia. 100.000, 1.000.000, 2.000.000, 3 million Z lutetium 5000.0000. Middle Stone Sea and Age. Upper Paleolithic A. Impiolb Paleolithic IMOUSTERIANJ. Poorly AA First. Chopper. Chopping tool. Complex 7 Copyright. Copyright Cloth 4. 2. 3 asterisk. 4 5 6 7. CLO 5. 2. 3. I asterisk 5 6 7. B. 6 6. 3x. 4x. SX. 6x 7x 8x 19x. OKAR. O. U. Pode.th. D. Pounds C. Dating methods WCLJ Stoies Heavy Ages. Figure 16.10 Chronology and the tempo of cultural change during the Pleistocene, in calibration of hominoid evolution. Gross culture stratigraphic entities are shown in relation to a logarithmic timescale after J. L. Isaac in Bishop C. Miller eds 1 C. 72, pages 381430. 395. Methodology and African Prehistory. I 960. 1920. Greater than I 880. Air temperature code WMC 010 1900. East Turkana Rudolph Kenya. The stratigraphy summed up in figure 16.10, which is due to Brock and Isaac 1974, concerns 325 meters of deposits spread over a period extending from about 3,500,000 to 1,500,000 years according to Bowen, Brock, Isaac and Vondra, 1975. Legend 1. Thermal MBXIMUM of 1942. Little Ice Age 3. Younger Dry AS Cold Interval for Present Interglacial Holocene 5. Last Previous Interglacial EMIANBTOLA IDIO 3 AS 6. Earlier Pleistocene Interglacials. 02.4680 C 900 greater than the last 10 teak. LATITUD air temperature. Or temp. I-20. 225 x 30. Global ice volume by milliliters asterisk. 4. 10 ccc the last 10 asterisk tears 10 cd the last tile tears. Low asterisk exclamation point asterisk. The UST 10 asterisk tears. Figure 16. I generalized trends in global climate for the past million years. A changes in the 5-year average surface temperatures over the region 0 to ADN during the last 2 years. Mitchell, 1963. B. Winter Severity Index for Eastern Europe during the last 1,000 years. Lamb, 1969. C. Generalized mid-latitude Northern Hemisphere air temperature trends during the last 15,000 years. based on changes in shorelines. Lamarche, 1974. Marginal fluctuations in alpine and continental glaciers. Denton and Carlin, 1973. And shifts in vegetation patterns recorded in pollen spectra. Van der Hamen et al., 1971. D. Generalized Northern Hemisphere air temperature trends during the last 100,000 years, based on mid-latitude sea surface temperature and pollen records and on worldwide sea level records. E. Variations in global ice volume during the last 100,000 years as recorded by changes in isotopic composition of fossil plankton in deep sea core. V. 28238. Shackleton and Opdyke, 1973. 39 degrees. Chronological framework, African pluvial and glacial epochs. Hadar, Central Afar Ethiopia. Finally, the formations at Hadar in Central Afar, which contain hominids and a wealth of fossils and which have been studied by the International Afar Research Expedition IARE, are 3 million years old according to Johansen and Tybe and others. 1974, 1975. In a few years' time, the work actively pursued in these parts of East Africa will make it possible to suggest another theory of climatic evolution based on sedimentology and plant and animal ecology, and taking into account the intervention of tectonic and volcanic factors. Intensive studies have been made of other parts of Africa, such as the Sahara. Aliment et al., 1959, Aliment, 1975. The Nile Valley. Van Dorf, 1968, Butzer and Hansen, 1968, D. Heinzelin, 1968, G. Gengak, 1968, said, in Chap Hoppins, 1965, Servant, 1973. And North Africa. The HE climatic variations proposed are based on the succession of sedimentations and bed lowerings of the Newark, or the successions of of fauna. Failing a radiometric or magnetostratigraphic dating, it is not yet possible to correlate these variations with the European glacial fluctuations. Conclusion. A feature of the Upper Cenozoic over the past 5 million years is the accentuation of the thermal gradients of the globe combined with considerable climatic changes in the course of time. This accentuation has led to considerable variations in temperature at high latitudes and hence to glacial and interglacial periods. At intertropical latitudes, thermal fluctuations were somewhat attenuated, but atmospheric circulations, disturbed by the strengthening or weakening of the polar fronts, brought about considerable variations in the distribution and quantity of rainfall, which helped to change profoundly the environment of the different climatic zones, periodically modifying the geographical and plant environment in which the fauna lived and in which hominids developed. These climatic variations establish the rhythm of the evolution of Africa more clearly than do the glaciations in Europe. What should be borne in mind in this brief survey of the state of our knowledge concerning climatic variations and dating in Africa is the need for continuing observations and measurements before fitting our heterogeneous knowledge into the rigid framework of a theory. On the other hand, we see the importance of the time scales of the various manifestations of climatic change. Care should be taken to place each observation and each phenomenon within the correct time scale. By way of conclusion, this is illustrated in Figure 16.11 taken from the volume of the National Academy of Sciences 1975, in which 5 examples of climatic variations are given for time scales ranging from a century to a million years. 397. Exo lutetium. Z. Lutetium. 001. V. Lutetium. -1. O. Lutetium. Z. Lutetium. UO. I. 0. 111. H5. V greater than, underscore, is, tilde, 3p, 3s, tfi, v. Geomagnetic reversals. Epoch. I is normal. F. Them a reverso. I. Reversed. 15. Then. R. Then. Event. LASCHAM. JARAM by LL. OLOUVAI. KAENA. MAM MOTI. COCHII. Nunavak. OLOUVAI 8 ASIN. 0. 10 Basin. TEKORAFM. LOTHAGAM Silk AANATOI Basalt. F. Lutetium. O. ** 3 degrees so LOT. East RUVO LFBASIN. ILEREDKOOBIFORA. ZOI, J underscore TUF circumflex accent TUF, S, ROTUF, U, OC30Z3, 1, GE, 0, USNO, formation, X, TU vertical line, then AALABONFM, MURSIFM, Bavaria delay, CHAMPEIX fauna, SOLILAHAC fauna, asterisk MALOUDEYRESINZELLES font slash, SENEVE fauna, Lee COUCE fauna, per Yeroki NEVR fauna, per Ye asterisk ETOUAIRES fauna, VIALETE, Northern Italy, circumflex accent asterisk plus Villafranca DASDI fauna, asterisk 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 I asterisk asterisk asterisk, America, IS1, 1, COSOMTNs, ZVON, Tahama, Hagerman -1, I1 white cone I, Z, -1, underscore J, Anol, X, O, HEM, 398, Figure 16.1 to radiometric and paleomagnetic aspects of the Pliocene-Pleistocene time range in eastern Africa, southwestern Europe and western North America. The very important successions afforded by exposures in the Ilha and QHI forest areas, East Rudolph Basin, are still under investigation and, as the results are incomplete, their respective columns have been left blank after Ed Clark Hull, 1972,